To our fifth webinar in our Train Talks at 12 series. I'm Jackie Butterfield. I'm the lead applications engineer for LB Foster in Europe. And today we will be looking at low adhesion issues. How it's formed, what causes it, what the impact of low adhesion is, and how friction management can help to mitigate against it. Today, the main part of the presentation will be given by my colleague, Dr. Thomas Butcher, who is also an applications engineer based here in Sheffield. Tom's been with the company for just under 2 years now, and prior to that, he was a researcher at Sheffield University and was awarded a PhD in the understanding and modelling of low adhesion in the wheel rail interface. So he is very much an expert on low adhesion. So I'll be here just keeping an eye on the chat and fielding any questions that you might have. So the agenda for today, as always with these webinars, we're going to start off with just a recap on why do we need to control friction in the wheel rail interface. And then Tom will go through the low adhesion issues. What is adhesion to start with, defining that. What is low adhesion, what causes it, how to control it. Some case studies on the impacts of low adhesion, and then go on to mitigation methods, including equipment and consumables, and then finish up with some case studies and a summary. So I'm now going, as with all these webinars, why do we need to control friction in the first place? So friction is critical to the movement of train vehicles. Without friction, there would be no movement. However, uncontrolled friction at the wheel rail interface may lead to issues. And some of these issues we've already covered in previous webinars, such as wheel and rail wear and rolling contact fatigue, corrugation and noise. Some we're going to cover in future webinars, such as high lateral forces and derailment, as well as energy consumption. But today we're going to be talking about low adhesion, which some of the issues are wheel flats, signals passed at danger, and also braking issues. So I'm now going to hand over to Tom, who will take you through the rest of the presentation.
So, hello everyone. As Jackie just said, my name is Tom Butcher, and I'm here to present this webinar on low adhesion in the wheel rail interface. So to start off, what are adhesion, friction and traction, and what are the differences? Friction, adhesion and traction are 3 words that are sometimes interchangeably used when describing friction in the wheel rail interface. Friction can be defined as the resistance encountered by one body moving over another. This definition covers both sliding and rolling contacts, because rolling contacts nearly always involve some sliding component, and therefore the 2 classes of motion are not mutually exclusive. Within the wheel rail interface, this is known as creep. So the friction force operates parallel to the direction of motion, opposing the applied force. If the solid bodies are in contact, the static friction force is equal to the tangential force required to initiate sliding. The kinetic friction force is the tangential force required to maintain sliding and is generally lower than static friction. The rolling friction is the force required to maintain rolling. So the friction coefficient is calculated by dividing the force used to initiate or maintain motion by the normal force. For wheel rail contacts, the railhead friction is usually broken down into high, intermediate, low and ultra low levels, though these thresholds can vary depending on other circumstances. Typically, high friction has a coefficient above 0.5, intermediate is between 0.5 and 0.2, low is between 0.2 and 0.05, and ultra low is below 0.05. There is much debate, but these are typical figures. LB Foster would usually consider a range of 0.3 to 0.4 to be intermediate friction. So how do we measure friction on the railhead? Friction can be measured with various tools, the most common being tribometers, which come in various shapes and sizes. Typical examples include push tribometers, which you can see on the screen, skid resistance tribometers, which are the simplest, and they use a spring-loaded rubber pad, which is released and skids over the railhead. This then pushes the needle up a scale to show a loss in energy. Portable rail tribometers are another option, which take a friction reading at one specific location. Another method for measuring friction involves instrumented wheel sets, though these are uncommon as they are extremely expensive. Rail friction can also be simulated in various ways and at different scales for laboratory testing. Low adhesion is almost always caused by railhead contamination, which usually consists of water, leaves, oxides, oils, fuels, greases, or a combination. Depending on the amount present, water is known to both reduce and increase adhesion levels. Small amounts of water, like you might get from morning dew or condensation on the rail, especially when combined with leaves or oxides, can lead to ultra-low adhesion levels. This is known as the wet rail phenomenon. Whereas if the railhead is saturated, then the friction can be brought back to intermediate levels. Large amounts of water can even help with softening leaf layers and softening oxide layers, allowing them to be pushed out of the contact. Oxide buildup can result in low adhesion levels. This occurs when oxidizing agents or chemicals are present on the railhead, or if it's been left overnight. Leaves on the line is a very notorious term when talking about rail low adhesion, especially in the autumn period. Leaves on the line cause the lowest friction levels when they've been run over by multiple wheel passes and the layer has been compacted and bonded to the railhead. Eventually, this results in a fully formed black leaf layer. You can see a very severe example in this image. When this black leaf layer is combined with small amounts of water, this will reduce friction to potentially dangerously low levels. We'll go over some case studies where this has been the case later on. The potential effects of low adhesion can vary. They can include wheel flats, wheel burns, signals past at danger or SPADs, delays, station overruns, and in the worst case scenario, derailments and collisions. The Rail Safety and Standards Board in the UK estimates the cost of low adhesion in the UK to be around £355 million annually. This is attributed to delay minutes, safety costs, and prevention management and cleaning costs. Clearly, the impacts of low adhesion have potentially devastating safety and financial implications. Low adhesion is often attributed, at least in part, to rail accidents and collisions. Some examples from recent memory include the train collision in October in Wales last year, as well as the one in Salisbury in 2021, the Sheffield tram crash in 2015, a buffer stop collision in Chester in 2013, and a station overrun in Stonegate in 2010, though there are many more. So what can we practically do about low adhesion? So, low adhesion mitigation. There are multiple ways in which the effects of low adhesion can be mitigated. Vegetation management is an obvious way, both by reducing the number of leaves and their proximity to the line. The risk of leaf layer development is reduced. Also, less moisture is trapped, allowing the railhead to remain drier for longer. This also helps with oxide buildup. One of the most common methods is onboard sanders, either single or double variable rate. Essentially, these apply sand through hoses to the wheel rail interface to increase grip and traction. One of the drawbacks of sanders is the inefficiency of sand delivery into the interface. The majority of the sand doesn't enter the contact and gets wasted. Also, over-application of sand can lead to wheel rail isolation and wrong side track circuit failures. Railhead cleaning can take the form of high pressure water jetting, dry ice blasting, and the use of chemical cleaning agents. There's also a change to the driving style of the train drivers, which are given adhesion forecasts to advise them on how cautious they need to be each given day. Finally, line side applied top of rail friction modifiers, such as Alleviate or another effective method for localized adhesion recovery. The traction gel applicators, or TGAs, are one of LB Foster's flagship products that are used to apply Alleviate to the railhead. Low adhesion and ultra low adhesion are obviously not desirable on the railhead interface. Here, the optimum level depends on whether the train is accelerating or braking, but typically 0.3 to 0.4 is ideal. Alleviate traction gel can be used to bring the friction to 0.4 and above. So, as mentioned in the previous slide, the TGA is LB Foster's current trackside traction enhancer applicator unit. It's an electronically actuated. It can be powered by main supply, solar panels, or wind turbines. The TGA applicator bars should be placed at least one wheel circumference before the effective braking or traction zone. Usually this is 1.5 to 2 meters. This is done to ensure that the leading wheels are coated with traction gel, which can be seen in the middle image, before braking or traction is required. TGAs are typically used seasonally from September to January and decommissioned before the winter season. However, they can be used year-round in locations where traction or braking is critical, such as steep gradients. Looking in more detail at the TGA, the cabinet contains a product tank, digital control box which controls the pump output and frequency, dual peristaltic pumps which are able to pump the abrasive traction gel. The unit can also be moved easily to another location if required. It can also be equipped with remote performance monitoring if the customer requires. So, Alleviate. It's applied using traction gel applicators. It's LB Foster's own formulation that has been developed over many years. It consists of a granular abrasive sand-like product suspended in a water-based gel. Once on the railhead, it has an effective carry down of approximately 150 meters, where it can increase the friction coefficient to intermediate levels. It's environmentally benign. It's primarily used in autumn due to leaf fall. It breaks down contamination on low friction materials, such as leaf layers, both on the rail and the wheel. It has low solid separation with a 21-month shelf life. The middle image shows Alleviate distributed on the wheel tread, where the sand is retained, but the gel has been expelled. So this means it's ready to go over a low friction area and increase the friction. Alleviate has been tested in multiple field and laboratory trials and proved to be effective in restoring adhesion levels. The graph on the left shows the results of twin disc testing, comparing a dry contact with wet leaves and Alleviate with wet leaves. This shows that adhesion is quickly recovered when used on a wet leaf layer. The graph on the right shows field trial data with the coefficient of friction levels for before and after brake testing with Alleviate with and without leaf layers. It clearly shows that Alleviate increases the friction levels. So now we're going to look at some case studies. TGAs have been used globally for almost 2 decades, with well over 1,100 units sold since 2007. They're predominantly used in the UK, which has over 1,000 units installed, though they have been installed across Europe, North America, Australia, New Zealand, and even Papua New Guinea. One example of a location that uses a TGA year-round is on the upline at the Tyseley Yard Depot in Birmingham. This location sees heavy freight vehicles between 1,800 and 2,000 tons. It has a steep gradient. They've had historical issues with vehicles slipping to a stand on the gradient. The issue is year-round and not just restricted to the autumn leaf fall season. The impact of the train failing on the gradient can lead to blocked access to the carriage sidings, which will restrict movement of empty coaching stock bound for Birmingham, New Street and Moore Street. And this will affect passenger services and increase costs, as we've shown in the previous slide. So they now have 2 TGAs running year round. The first was commissioned in December 2021, the second in August 2023. Prior to installation, the annual number of non-autumn related traction problems were between 1 and 3. After the installation, this number fell to 1 a year at most. So, in summary, we've gone over the definition for friction, adhesion and traction, talked about the differences between the three. We've talked about the causes and effects and mitigation methods for low adhesion. We've talked about the TGA3 and alleviate that it uses, as well as looked at a case study for year-round deployment. I'll hand back over to Jackie now to talk about the upcoming webinars in the series.
Thank you, Tom. So, as Tom said, we still have some forthcoming train talks at 12 to come. So the next webinar will be on Wednesday, the 5th of February, and that will be on energy consumption. And at that webinar, I'm going to be joined by Matt Holland, who is our Global Product Manager for Onboard Solutions. So he's going to be primarily talking about our onboard top rail spray system, KOB, as this can be used very effectively for lowering energy requirements for rail, both transit and freight vehicles. Following that will be on Thursday, the 6th of March, which I will be talking about derailment risk. So how friction management can be used to prevent different types of derailment, both high lateral force derailment and also wheel climb derailment. And then our final webinar will be on Wednesday, the 9th of April, and that will be a bit of a roundup session looking at validation and trials best practice. So how do you ensure that the friction management solutions that you're employing are actually giving you the benefits that you want? And that will conclude our webinar series. So all that is left to do is thank you for attending today. And if you have any questions, then please pop them in the chat and we will be happy to answer them for you. Just open the chat. Does anybody have any questions today? Oh. Potentially have a question coming. Oh. Thank you very much. You're very welcome. Okay, if nobody has any questions, then I will let you get on to your lunch or your other meetings. And I look forward to talking to you next month.
Yeah, thank you for listening.
Thank you. Bye.
Bye.